We're live. All right. Hello, all 6 of you. Welcome to Comp 3430 Operating Systems. I spent an embarrassing amount of time getting the snow to show up in my slides today. I thought that would be appropriate for the outdoor situation that we're currently in. I can't take credit for actually writing the code. This is more of an integration thing, but yeah. I hope that you're all doing okay today. I hope that if you're watching on the stream that you're also doing all right. What I want us to be able to do by the end of today is kind of the same stuff that we've been doing for the previous couple classes this week. My focus today is I want us to finish taking a look at the internal structure of our virtual address space. So what we've been looking at so far has really been trying to ground ourselves and make sure we have a good sense of what the internal state of our address space is, and that we're able to make confirmation that the description of virtual address spaces that have been made to us over the years is true. Like we can actually confirm that the code section is at the top and the heap is below that and the stack is at the very bottom of our address space. I want to take one last look at this, and then what I want to do is start thinking about how we can try to cram these virtual address spaces into physical memory. So how do I take a running process and how do I jam it into the machine's memory that I've got in front of me? So we'll take a look at both of those things in today's lecture. But before we get to that, it's Friday. It's Friday, and so I want to take a little bit of time to take a look at where we're going next week. So next week is week 12. There's 13 total weeks in this class, so we're getting real close to the end of the course. What we're going to be looking at next week is memory segmentation. So one of the things that we're going to find out in today's lecture is that the basic approach to doing virtual memory is deeply flawed. It worked 50 years ago, but it doesn't really work now with the kinds of systems that we have. And so we're going to look at some of the issues that we have with the basic implementation of virtual memory, and then we're going to move on to trying to fix those problems with this idea of segmentation. And really, really briefly, the idea of segmentation is to take these 3 segments that we've identified, our code and our heap and our stack, and just allocate those separately as opposed to allocating an entire address space. That's just going to lead to different problems. We're going to have problems with what we're looking at now, and we're going to have different problems. And one of the wild rides that we're going to be able to take next week is figuring out what's actually happening when the word segmentation fault gets printed to our screen, and who has the responsibility of actually printing that to our screen. There's 2 chapters that we're looking at for next week. There's segmentation, and there's free space management. I want to take a quick look at the segmentation chapter, and I want to look specifically at one part of this because I want to make clear that I don't actually care about this one part of it. So there's a little aside here about the segmentation faults, but we'll get to that. We'll get to that next week. There's one part here in terms of the stack as a segment in this chapter where I'll let you look at this, but I want to be clear that I don't care too much about the hyperfine details about this section. The thing that's described in this section, and this is section 16.3, is a little bit about how virtual addresses are translated to physical addresses in the context of the stack itself. And the calculation of this has to be like backwards. For good reasons, it has to be backwards and inverted from what we're normally thinking about as the way that we're doing address translation. But I don't actually care about you actually being able to calculate addresses in the stack using segmentation. So like if you don't quite get the idea of translating these addresses for the stack specifically, I really don't care. I'm not going to ask you questions like that. I'm not going to ask you to translate addresses on any kind of test. So when you get to this point, I'm giving you a little bit of forewarning that there's a bit of a like it's unclear how this works unless you spend a lot of time thinking about it, and I don't find that valuable. So don't spend a lot of time thinking about it. Don't dwell on this part. The other chapter that I'm asking you to take a look at is this free space management chapter. In free space management chapter, what we're really going to see is that this is related to segmentation in the sense that the segments that we're looking at are different sizes, but in modern computing and modern virtual memory implementations, this is actually a heap management problem as opposed to an operating system's responsibility. This chapter is 18 pages long, but I want to go through this and quickly show that there are almost full-page diagrams in a lot of cases with this part of the text. These diagrams take up an entire page. They take up an entire page. So in terms of the stuff that's in here, the diagrams are taking up quite a bit of space. So we'll get to this all next week, but I wanted to give you a sense of that, and I really wanted to call out this specific section in the segmentation chapter, as I know that it's not exactly straightforward, and I don't actually care that much about it. So when you're getting to this point, just keep that in mind. The other thing I want to do before we get to stuff today is to give you a chance to ask some questions about assignment 3. So I'll leave this up on the screen for a couple seconds if you want to do that. And while you're getting connected to that, I'll start it because I realize I haven't started it. Forgive me for doing that. I'll start it. And while you're doing that, I'm going to go back to my slides here. And there's one thing that came up on the course forum that actually happened to me when I was implementing this, and I wanted to call it out just because I want to make sure that nobody else is getting bitten by the same kind of problem. So the observation that we were seeing on the forum was that we were getting into a state where we were having our contexts doing swapping, but every time they would come back, it looked like there was no progress being made. So the state of that thread was not being continuous. The thread would start again, and we could switch between them, but each time the thread would start, it looked like it was just starting from the beginning again. So starting counting at 0 as opposed to starting counting at wherever it happened to be left off. And the problem ultimately boils down to unintentionally copying the context, I did this consciously and intentionally, but I didn't realize what I was doing when I was doing it, and it was kind of like an unexpected mistake. When I was doing this, I was actually using memcopy in my queue code to copy the thread control block into the queue so that I didn't have to worry about the one that's in the queue, that was outside the queue. But then by copying it, I was kind of doing this thing every time I would enqueue it, I would copy the state that it is right now and then just overwrite that state and then copy that same state and then never actually get updates. The context that we were seeing in the other place here was, and this is actually something I've seen at least one other time, unintentionally copying the data in a structure to a stack allocated variable. So this line right here, the declaration of this is that it's a stack allocated structure. So it's not a pointer to a stack instance. It's not a pointer to a struct instance. It's a full thing on the stack. And so what's happening with this line is if this is an instance of our thread control block structure, and then this is an instance of uContextT inside of that thread control block structure, that line it's not giving us the address of the thing that's in our thread control block, it's copying the contents of the struct. And so what's happening on this line beneath that is that swap context's first argument is the context that we want to put the current state into, but context itself is a stack allocated variable. And so we're writing the changes, we're persisting the state of that thread into this stack allocated variable, And then when the function returns, the stack allocated variable gets popped off the stack and it's gone. And so the thing that we would then enqueue later or put onto the stack, put onto the processor later, this next context that we're getting from our queue is just the original one that we had. Yeah. So this TCB here, this is a pointer. This would be a pointer. So because this is a pointer, we need to use this dereferencing operator to get access to its properties. But this itself is not a pointer. So the property itself would just be defined as uContextT inside that structure definition. And then this one here is not defined as a pointer at all. It's just a straight stack allocated variable. And doing assignment with structs in C is you copy them. This is something that I forget all the time because that's not what happens in Java. When you do this in Java, when you assign objects to each other, you're just making copies of the reference. You're not actually copying the content of the variable. But if you're doing a stack allocated structure in C, you're doing copying. You're doing a deep copy of that object as opposed to just doing a reference to it. And that's where I think the problem is here. We're assigning the context to the stack allocated variable, persisting it to the stack allocated variable, and not this thing anymore. And we're just chucking it out at the end. And so every time we re-queue or reload this context, it's just going to be the same one that we originally got from the get context function. I sort of thought that this might be like there's magic happening. When I was thinking about this originally, I sort of thought maybe there's some magic happening here that we don't know about. And maybe there's metadata outside of the context object. And so the manual page for get context describes uContextT here, importantly as opaque. So we have some idea of what this structure might look like, but it's not something that we should know the internal implementation details of. The manual page for get context describes the structure looking like this, but it doesn't really say like this is actually what the structure is. It's just saying you can expect these fields to be in this structure when you work with it. Metadata for objects can exist outside of the structure that we have access to when we're given a pointer to a structure. So I want to give an example of what I mean by that here. Here is an example, an instance of a structure that has been defined, and that structure contains an instance of a pointer to this uContextT, but there's extra stuff in the structure that's around it. But a function that gives us access to that internal part could be giving us a direct pointer to the inside struct instance. And so there could be extra metadata here. And so what might be happening, what I imagined to be happening when I first thought of this was that, okay, well, if we're doing structure copying of just this, we're not copying more stuff here. There's extra stuff that might be related to this structure outside the context of the structure that we have access to, and we're doing this copying. But I more realistically now think that what we were seeing is that we were just doing this to a stack allocated variable. So we weren't actually persisting changes to the global state thing that we had. We were just doing it to a context that was on the stack. All right, okay, so I'm gonna pop over here. If threads can be created after all have been joined, how would we know when it's ending to clean out memory, or do we not have to worry about that? I think I'll probably just say you don't have to worry about that. In theory, the main thread should have control, and then the only way that it would be able to tell us that there's more threads after all the threads have finished would be for the main thread to yield itself. But I'm not going to contrive a situation like that. I'm not going to call NQP thread create in main after all the threads are joined and then call yield. You can just assume that after all the threads have been joined, we're just going to shut down after that. All right. Okay. There's no other questions. Awesome. How is it going? Like, is it going okay? So far, there have been many fewer questions on the forum, but I can't tell if that's because there's like software engineering stuff due or comp org stuff due in the next coming week, and we just haven't gotten to that yet. Things are going okay? Awesome. Well, I'm really happy to hear that. Okay. All right, let's pop back here. So I want to talk about virtual address spaces again. Again, the idea that we've got with spending so much time confirming what our virtual address space looks like is I really want us to get a sense of what it looks like from the inside before we start trying to take what's on the inside and stick it somewhere on the outside. And so last class, we spent a little bit of time running this addresses.c program. And again, this is up in that repository if you want to take a look at it. I kind of realized after the fact that I would be interested to know approximately what the output on this is from a Mac. So if you have a Mac, I'd be interested to see if you have this address space layout randomization effect showing up. I believe that Mac OS does this, but I'm not 100% sure off the top of my head. But when we were running this program, we were ultimately able to see that on my actual physical system here, the addresses for each of these things, while remaining the same in a relative sense, we could always see the code was at the top and the heap was beneath that and the stack was at the very bottom. The actual addresses of this changed every single time that we ran it. It changed every time we ran it. And this was this security solution to try and make sure that an attacker, someone on the opposing team, is not able to know necessarily where our main function is in memory. So they don't have an ability to inject more code to be executed here if they were able to do something like buffer overflow exploits. On old systems, and I brought up a virtual machine to show this, on very old systems, Linux does not have address space layout randomization. And so we were able to show that the process that we would run every single time it ran would have this predictable address for where the code segment is, and it would have this predictable address for where the stack is at the very bottom of the address space. What I want to do now, sorry, I'm looking up here to see if either of you happen to run that code while I was up here rambling on with your Macs. Do you know if you get different addresses every time you run it? Did you try? All right, I'll just accept that. Yeah, okay. And then I see a big nod. Yes, it's happening. Okay. So the other thing I want to do is dwell just a little bit more on this file. This is procpid-map. So this is in the proc file system. And there's this file here that's called maps that contains the address mappings of the process that happens to be running right now. So I'm going to take a look at this addresses.c program again. I'm going to run it once here. And what I want to do is I'm going to pop open proc 414 here. And I want to look at maps. This file, I'm going to zoom out just a bit. I'm going to zoom out a lot, and then I'm going to zoom in to, so that we can see the parts that are important here. This file shows us what the address space layout looks like for this process. And so at the very top of this, what we've got is there's like 5 copies of the program addresses that have been mapped into our address space here. This is the code section at the very top for the program that we've got. Beneath that is the word heap, and it has been put into this spot that's beneath the code section. And then at the very bottom here, we've got this, this stack representation. I'm going to zoom in again. And what I want to show is the column structure that we have here. So I'm zooming in really far because I want the columns to kind of show up on their own. The first column that we've got here is going to be the range of addresses in the virtual address space. So this is the range of addresses within the virtual address space where this thing has been loaded. We've got like 5 copies of the same program that are being loaded into slightly different virtual address areas here. They're all kind of like one after the other, and we're getting about 0x1000 out of each of those copies. The second column in this file represents the permissions that are attached to what we've loaded into this virtual part of memory. So the very first region that we've got here is read only. We cannot write it and we cannot execute it. It is read-only memory. So if we try to execute anything in that area or we try to write to anything in that area, we would get like a segmentation fault. That's ultimately what would come to our process. The second mapping here is readable and it's executable. The third section is only readable. The fourth section is only readable. And this fifth section here is readable and writable. And that seems kind of maybe weird a little bit. Like, why would I want to make changes to the code section? Why would I want to be able to make changes to the code section? That actually seems like it might be a little bit risky to be able to make changes to the code section, because the code section is ultimately what my processor is looking at in terms of running instructions for my program. If we go down a little bit further, we're going to see things like the heap is readable and writable, but it's not executable. And then down at the bottom here at the stack, it's also readable and writable, but not executable, which makes very good sense. I do not want to execute things that are on the stack, and I do not want to execute things that are on the heap. I just want to be able to read and write that. It's just memory that I want to be able to read and write. But this one section up here that is inside my file, that is readable and writable, that sticks out a little bit like a sore thumb to me as something that probably shouldn't be there. And it doesn't exactly make a lot of sense immediately why. So let's look at the third column. The third column here is an offset. This is an offset into the file, not the address space, but this is at offset 0 in the file addresses. This is at offset 1000 in the file addresses. This is at offset 2000 in the file addresses. This is at offset 2000 in the file addresses. This is at offset 3000 in the file addresses. So now thinking back to file systems, when we were working with exFAT, we were doing things like trying to get to different offsets within that file to be able to find things like where the FAT starts and where the cluster heap starts. And we were using hexdump with ext2 to do things like, let's find the superblock for this file system by moving ahead to this location. These offsets are the same as what those offsets are in terms of the file systems that we were looking at. But these are representing parts of the program that we have here as opposed to the file systems that we were working with. So this takes us on a slight digression. And the slight digression here is going to be to this Wikipedia page that's called the executable and linkable format file format for program files. ELF is the file format that's used to represent programs on Linux and Mac OS, possibly, depending on what version of Mac OS you're using. I think it's Mac OS. It's not important. It's definitely on Linux. The small joke here is that with file formats, we have ELF for programs, and then we have Dwarf for debugging files. That's the stupid joke. But this is a file format. It's a file format, and this file format consists of a bunch of different parts, kind of in the same way that our file system consisted of a bunch of different parts. Within an ELF file, there are going to be a bunch of sections here. The sections are going to be things like code. These are the instructions that are used in our program that our compiler spits out that represents the code for our program. There's the data section, which is going to be things like the file scope variables that you declared in this program. And the data section here is going to start somewhere within this file at some offset. The offset might be different for each ELF file that you are looking at, but I'm going to take a look here at offset 3000 in this file. So I'm going to zoom in here. I'm going to do hexdump -C on addresses. I'm going to pipe this into less, and I'm going to go to offset 3000 in this file. So offset 0 here, this is that first part. This is going to be ultimately something that gets loaded into one of those locations. And at offset 3000, there's a bunch of data here. There's data that we didn't write. Like, I didn't write this stuff into my code, GCC, Ubuntu, Clang version, and stuff like that. I did not write that into my own file. But these are strings in my file. I'm going to keep scanning down here. And what we're ultimately going to get is stuff like, here's the entire path of the file that represents this thing. I have array size. I have this thing called hello. I've got main. These are the names of functions inside of my program. This is a bunch of debugging information that happens to be in here. And this is data. This is the data that's in my program. And so that segment that's getting loaded into my virtual address space at that location, it's readable and writable because I want to be able to change things like file scope variables, which we don't necessarily see here, but I want to be able to change things like file scope variables that are in my data section. And the best way to do that is to just load that section directly into memory and call it a writable section. It's not in the stack, it's not in the heap, it's just kind of floating up here in the data section for my file. And so I think that's pretty cool that we can take a look at this running program, we can see what its virtual address space mappings are, and then we can go back to the file itself and see, oh, this is actually the data section that's being loaded into this part of memory. I put up on the course webpage a link to this wiki page. So if you do want to take a look at this on your own time, you're more than welcome to, but this is not something we're going to be thinking much more about. But you can see that there's a file, there's a table here that kind of represents this file format structure. And at this point, in terms of what you were doing with file systems, you should be able to write some code that would read this. You could read this stuff with the knowledge and the tools that you've got right now. The other thing that I've posted up here is a link to a manual page. This is the procpid maps manual page that describes the structure of the different columns that are in this file that we're taking a look at here. The two columns I didn't really look at here were dev and inode. Dev is kind of far outside the scope of what we're thinking about. Inode is, well, it's literally the inode in the file system that represents the file that we've got maps into memory at this location. All right, okay, so that's awesome. I don't know, I love this stuff. Like, I love that Linux is giving us this ability to be able to take a step into actually looking at what memory is for this thing. The one last thing, and I'm just gonna hand wave at this and I'm not going to run it, is if I were to go to the proc file system 226.414 and take a look at the contents of this directory, there's one additional file in here that we could look at. I'm not going to look at it. This is mem. If I were to start reading this file, I would need to use something like hexdump, but this gives me the ability to read the contents of memory for this process. This file represents the virtual address space for the process that happens to be running right now. I need to be root to be able to read this file, so you can't read this on Aviary. You don't want to be able to peek into what other people's processes are. But if you did take a look at this using hexdump, you have to use offsets and stuff to make sure that you're only reading parts of memory that have actually been allocated. You get I/O errors instead of segmentation faults, but they're approximately the same things here in terms of what's in this file. But it's cool. It's really awesome to be able to see this stuff. So at this point, we've kind of seen like we've got virtual addresses, and it matches what our mental model is for virtual address spaces. We have this code section. We've mapped this file that represents our program repeatedly into memory in the code section, we've got the heap beneath that, and we can see that by calling malloc and looking at the address and seeing that the address is beneath the code section. And we've confirmed approximately that the stack is at the bottom because we allocated the stack variable and we took its address, and it's got this really, really big address that shows up at the bottom. And then we were further able to see that the Linux kernel shows us what the address space layout is for this process, and we can see that, yes, the code section is at the top, the heap is beneath that, and the stack is at the very bottom. But the problem with all of this is that the size of that virtual address space with those really huge numbers that we have there is much, much, much bigger than physical memory on my machine. I had to look this symbol up. In LaTeX, this is a GGG symbol, much, much, much greater than. On a 64-bit address space, which is what we're looking at, I'm hand waving here. We're not actually using all 64 bits for addressing on these systems, but if we were to use this 64-bit address space, it would be exabytes of memory. And the physical memory that I have on my machine is, I got 32 gigs, which is admittedly a lot of memory to have on a laptop, but it's nowhere near exabytes. And the problem really is that in my system right now, I'm doing ls in the proc file system, and my window is not big enough. Like, I zoom out, and there are so many processes running on my system right now. I'm going to zoom back in, and I'm going to run psafx. So this is printing out all of my processes. It's printing out a full listing. It's printing out X's like the tree shape, so it shows us which process has which process is a parent. And then it's printing out the entire path of these things. So you can see the relationship between these two processes is that this one is the parent and this one is the child. But this gives me a full listing of the processes that are running on my system. And if I pass this to word count, I've got 624 different processes that are running on my system. I'm gonna approximate this. We've got 600 processes running on this system right now. If I were to take 32 gigabytes of memory and divide that by 600 processes, they're each going to get about 50 megs of memory. If we were to actually fully subdivide the actual amount of space that I've got here. But every single process has this many exabyte size of virtual address space. So how is it going to work? How is this all going to work? The thing that we really want to do here is that if this cat is our virtual address space, and if this egg carton is our physical memory, we want to be able to put more cats in our egg carton. That's really what we want to be able to accomplish here. So the idea is that rather than trying to put the entire virtual address space into physical memory for a process, let's just make the virtual address space smaller. That's our first idea to support this idea of virtual memory. Rather than trying to support 16 exabytes or whatever of an entire virtual address space, let's subdivide physical memory into smaller chunks and then put our address spaces into there. So let's visualize this. Let's take the time to draw some pictures that represent something like what this looks like. I'm going to say this. The diagram that I'm drawing here is for my computer. And I'm going to draw this in that kind of abstract representation of what we think about when we're thinking about memory, which is a big box. It's going to be a big box. I'm going to draw this out as my actual machine here. And I'm going to say that this is my physical memory. And I've got starting at 0 gigabytes all the way up to 32 gigabytes. I want to take this address space that we've got for these processes, and I want to be able to cram it into this actual physical 32 gigabyte space. And so my idea is that I'm going to take the amount of physical memory that I have, and I'm going to subdivide it. I'm going to break it into smaller pieces, and then I'm going to give each process that much space. So my idea is that each process gets a quarter of physical memory. And so I'm going to have a process here. I'm going to call this PID1. This is maybe Firefox running on my system. Got process 1 that is Firefox. And Firefox is going to get an address space that goes from 0 gigabytes up to 8 gigabytes. It's a quarter of physical memory. I'm just going to constrain the size of the virtual address space that I'm giving out for this thing. The layout of this address space that I've got for this process is going to be the same as what we have observed with the system that we've got now. I'm going to have a code segment. I'm going to have a heap segment. I'm going to have a stack. The heap will grow down and the stack will grow up. I'm going to have another process. This is the terminal that I'm using, Ghosty. This process is also going to have some subdivision of the physical addresses that I've got. So this is going to be 0 gigabytes. It's going to go up to 8 gigabytes. It's going to have its own code section. It's going to have its own heap. And it's going to have its own stack. So these are 2 of the virtual address spaces that I'm going to have in this setup. So Firefox will be given permission to have addresses that are between 0 and up to 8 gigabytes. That's the amount of memory that it's going to have available to it forever. Ghosty is going to have from 0 up to 8 gigabytes. That's the only amount of memory that it's ever going to be able to have. And I'm going to take each of these and I'm going to jam them into physical memory in different locations. So I'll take Firefox and I'll stick it up here, and I'm going to subdivide my memory into 4 chunks. So Firefox's code section is going to be up here. We'll have code. We'll have a heap. And we'll have a stack. The heap will grow downwards. The stack will grow upwards. Ghosty is going to be jammed into this physical memory location. And it's going to have its own code section. It's going to have its own heap. And it's going to have its own stack. The heap will go down. The stack will go up. There's a couple problems with this. The first, I hope, is immediately obvious to you. It can only run 4 processes. And that clearly doesn't match the system that I've got right now, in that I have hundreds of processes running on my actual system. I could subdivide memory even further. I could divide this 600 times, but then each process is only going to get 50 megs of space. And that might actually be okay for Ghosty. It's definitely not okay for Firefox. It's definitely not okay for Chrome. The other really big problem that we have with this setup is this region right here and this region right here. Within these processes, I've allocated this entire block. So like this whole thing has been allocated to Firefox. The entire chunk has been allocated to Firefox. This whole thing, the entire chunk has been allocated to Ghosty. But this region that we've got that's lying between our heap and our stack, for Firefox and for Ghosty, it's unused. Like we've allocated it, but 8 gigabytes is a lot of memory. 8 gigabytes is a lot of memory. And yes, while our web browsers do tend to use up a lot of memory, in practice, things like Ghosty, my terminal, they're using such a small amount of memory compared to this, even hundreds of megabytes of memory. If they're using hundreds of megs of memory, we're going to be wasting a huge amount of this 8 gigabyte range that we've given to this process. The worst part of all of this is that it's possible, if I were to take these and add them all up, that I might be able to fit another process in, or another 50 processes in, or another 100 processes in. This idea where we have these allocated spaces that are not used by what has allocated them, this is called internal fragmentation. Fragmentation is a word you have seen before. Fragmentation is a word you've seen before, but in the context of file systems. And this is our first hint that the things that are the things that are used for file systems are also problems in memory in terms of managing memory. And the idea of working with file systems and memory becomes pretty closely related ultimately. The structure that we will eventually see with paging is approximately going to be an inode structure with indirect block pointers. Yeah, it's cool. It's really cool. So with this basic approach here, to give you a title for all of this, this is described in our textbook as base and bounds. We will keep track of where each of these different allocations lie in physical memory, and as those contexts are being switched to for these different processes, we'll reconfigure the hardware to say you should start here for a virtual address space 0, and you can go up to here for the biggest virtual address in this process. This is base and bounds, but now we've got this big problem where we've got internal fragmentation, and we've got this big problem that we have a fixed number of processes that we can run in this system once it starts up. Are we all okay with this? Yeah. So internal fragmentation is that this part of the address space that we've allocated in physical memory here, this part is allocated by this process, but it's not actually used by the process. So there's a bunch of space. Imagine if we had a string in memory that was containing the characters HELLO, but you called malloc and you said, please give me a megabyte of space. That would be a good example of you causing internal fragmentation in your own program. Here, we're allocating 8 gigabytes of space for each of these processes, but the processes themselves may not actually use up the entire 8 gigabytes of space. And in practice, they're going to use so much less than 8 gigabytes of space that there's just going to be this giant chunk of memory in the middle of it that's been allocated for the process to use, but it never actually uses it. All right, so I will post a copy of something that looks like this up on the course webpage, but this is also in our textbook in a couple of the figures that we have for the basic introduction of virtual memory. Summarizing here is the problem that we've got is internal fragmentation. And internal fragmentation is very much this idea that we've got these allocations that have been made. The allocations are fixed in size. This is important for this initial thing. The allocations are fixed in size and they are all the same size as each other. And we're subdividing main memory to decide what the size of those allocations are. But there's going to be a big chunk of memory inside that allocation that's not actually used by the thing that has allocated it. And so then we've got this extra space that might add up ultimately to being big enough to fit something in if we were able to take that memory back from the process that we've got. This is a problem. This is an issue that we want to solve. We don't want to allocate this big chunk in the middle anymore. And this is what's going to lead us to segmentation next week. The basic premise with segmentation is that rather than allocating an entire address space, we just allocate the segments and we allow these segments to be different sizes as opposed to being fixed at the same size. But there's problems with that in and of itself. So at this point, you should be able to explain how an entire address space can be provided or supported by the concept of virtual memory. So this is one implementation based in bounds where we just subdivide physical memory. We put entire address spaces in and we just make the address spaces much, much smaller than they were before. Describing how the operating system works with the underlying hardware to manage virtual memory. In this case, with base and bounds, our operating system's process control block will need to have 2 extra fields. It needs to have where in physical memory this process's address space starts and how big it is. How big it is might actually be a system-wide property. It might not even be part of the process control block, but that's kind of an implementation detail. And the responsibility of our operating system here is going to be to tell the hardware when I do context switching, this is where virtual addresses start. This is virtual address 0 in physical memory for this thing. That's it for today. I hope that you all have a great weekend. I hope that this snow melts fast and there's not a lot more today. But otherwise, yeah, I hope that you have a good weekend and I'll see you all on Monday. Bye, everyone.